Okay, my name is Pete Swan. I've got a lot of credentials, mainly because I'm old. You do a lot of things in your life, so then you can write them all down. The real kicker is I've been in space stuff for about 50 years, and I've done mega projects most of my career. So it's not scary to work on mega projects. Once you get through the first one, you figure out that there aren't too many answers. You just keep charging ahead. But anyway, my background is management of big programs and stuff like that. I got a PhD in engineering, but I've forgotten more than I ever learned. So we won't deal with that too much. Okay, what I'm going to do today is I'm going to talk fast and show a lot of charts. Try not to read all the charts. If you want, send me an email and we can send you the charts or Dropbox them to you. I'm going to put my email address in there if anybody wants to follow up, and that way we don't have to worry about reading the charts during the discussion. You can just send me an email and I can work you some charts or something. What we're going to talk about today is the Galactic Harbour and how it's matured from space elevators, but really how it fits in the Econosphere between the Earth and the Moon and Mars. So welcome to the future. We're really talking about a routine, inexpensive, environmentally friendly, and daily liftoff of payloads towards space. Today, we'll explore the Galactic Harbour, and that will stimulate commercial enterprises throughout the ecosystem, and definitely stimulate movement off planet by people. Today, the basic question to be addressed, and by the way, there are no answers, so we won't have an answer, but we can start discussing it anyway, is should the Galactic Harbours be built by the government? Or should it be a public-private type activity? Or should it be purely commercial? Now, we've got a lot of examples on all three of those in the space world, and nobody's really come out and said which one's the right one for space elevators, but it's a heck of a question, and we ought to address it. But first, let's start. Now I got to figure out how to advance my thing because I covered up. Okay. First, we want to look at 2019. It really was a breakout year for space elevators. We moved to the Galactic Harbour because it has a bigger vision. We moved from wishing for a material. We spent 20 years looking at carbon nanotubes, and they just haven't lived up to their promise. But now we have a material in the lab that will work. Single crystal graphene, and then there are about 2 or 3 other materials also that have the same characteristics. I have about 5 charts on those a little later, but just believe me that the material is in the laboratory that can be long enough, 100,000 kilometers, and can be strong enough, 100 plus gigapascals. So we're really looking at a material that will work. We used to have an immature plan in the engineering side, but the International Academy of Astronautics put out a book and a 4-year study looking at all the technologies in a space elevator. And we came to the answer that we're ready to start doing segment testing, not the big segment, but all the parts to it, the technologies in it to move it to the level that we need to. And we recognize that the Galactic Harbour strengths, we've recently recognized 3 new strengths that the Galactic Harbours will enable off-planet migration. Okay, so the story is still being written, and that's why you're in the process of listening to the story here. The apex anchor is where the Galactic Harbour meets the shoreline of outer space. We really do have a harbor. And it's where the transportation story of the 21st century meets the final frontier. We truly are at that breakout year for space elevators. And we're going to be there actively pursuing many different things. Okay, what we're going to talk about today, we're going to give you some background on Galactic Harbours, where we are, what we're doing. We'll talk about movement to commercial space. Then we'll look at the space elevator development question that I posed at the beginning. Will it be commercial? And then we'll have time for questions and answers. And I'll leave back 15 minutes for that. So we, even if I don't get finished with the charts, I'll pick a few at the end and go fast. Okay, what's going on in the exploration world today? Holy Toledo, it's hard to keep up. NASA just executed a contract for 3 teams to work on the landers, human landers on the moon. The Chinese are charging ahead. We have lots of activities. Bezos has promised to deliver any package to the surface of the moon. Actually, he said anywhere, including Mars. I just saw in the news today that he should be a trillionaire by 2026 when he's on the moon. He might run it all from the moon, who knows? Anyway, so the current world is very much thinking off planet. And they're thinking commercial. Here's the numbers that I really like. Turned out in 2011, NASA did a study looking at Elon Musk and his building of the Falcon 9. And they said, well, if we were going to build a Falcon 9, and they gave the specs for, you know, what Elon Musk wanted for a Falcon 9, this is what NASA said it would cost them. $3.5 billion for R&D, and the total program would be $4 billion. You know, it's really amazing. SpaceX actual numbers, less than 300 million to develop it, and just about 10% of the total cost. That's the difference between commercial and government funded activities. Now there's 47 other dimensions to that whole question, so we won't go into all those right away, but they are interesting. Here's a comparison of Ariane 5 and Falcon 9 basically today. Maybe it's a year old, but it's basically the same. 62 million for a Falcon 9 and 178 for an Ariane 5. Now they carry a little bit more payload, so you know it reflects, but not that much, not 3 times. So the commercial world is out there living well. And let's not forget failure rates for rockets. We're not going to say that we won't have problems on a space elevator, but let's not think that the rockets are perfect. They have their problems as we go along. Okay, this is just for illustrative purposes, trying to define government contractor, public, private, and commercial. And we've got plenty of opportunities to look at all those over the years. Many of them work, many of them have problems. Here's a public-private example that's ongoing today. In fact, 2 weeks from today, hopefully, SpaceX will deliver astronauts to the space station. It was done under a public-private. Essentially, a public-private is where the public pays for the high R&D development, and then the private moves in to run the operations and the long duration, you know, the long-term type activities. Current big question in the House and the Senate in the US today. I love this. I was curious when I saw this starting to develop. NASA has executed a contract with Blue Origin, Dynetics, and SpaceX to design landers for humans on the moon. And this contract will fold into, you know, down selecting the landers and all that kind of stuff. The public-private partnership is alive and well in a concept like that. Bernice Johnson from Texas is really kind of questioning whether the US government should do a public-private type activity for something like this. She's tending toward it ought to be all government, a la the SLS. Oops. Then NASA just announced that they're buying a whole bunch of SLS motors at 99 million a piece, 2 per flight. So that's $200 million just for the engines. That's a wee bit high, but it's still, you know, the government approach. Okay, what is this? It's a beautiful little demo of commercial space building something for the future. Jeff Bezos built this and then he showed it off at the International Astronautical Congress in Washington, DC. And it really is an awesome capability. The rovers on top are much larger than the rovers on Mars, but they're smaller than the rovers that we had humans in on the moon. So they had 4 of them up there on the top. They can fit 4 of them up there. So literally this lander is far more capable than the lunar landers we used in the old days. Okay, where's the Galactic Harbour today? Whoop, I went too fast. Let's see if I can go backwards. Yeah, there you go. Shoot. Oh, okay, there we go. Back. Okay, the Galactic Harbour, where is it? It's a 2 space elevator business venture in one location. You put the first one up, and the first thing you do immediately is put a second one up, because you don't ever want to get caught by gravity again. And it's a business enterprise. So it's made up of many components, but let's talk about the strength. Everybody in the space business has seen charts like this: 9.3 kilometers per second to get into low Earth orbit, and then 4 more kilometers a second to get to GEO, and essentially the same to get to the moon, and a little more to go to Mars. But if you get on a space elevator and climb it with electricity, you get up to the top, 100,000 kilometers, and you're going 7.76 kilometers per second. And you can go to Mars and beyond, free of charge, no chemistry required. Oops, you do need chemistry to get the right trajectory to Mars, and you do need to slow down when you get to Mars. So definitely rockets are a friend of ours. We just don't want to use them to get out of the gravity well. Here's the bottom of this Galactic Harbour. It's 2 elevators separated by roughly 40 kilometers. Pick a number, any number you want. And you've got an ops center, and you take your products and you bring them in from ships, and you load them onto tethered climbers, and up they go. At the GEO node, we have a phenomenal capability. You deliver product to GEO very inexpensively, $50 to $100 a kilogram, something like that. And so if you're going to do that, you can start all kinds of entrepreneurial businesses at GEO. You can refuel, repair, put new solar cells on, construct satellites, et cetera, et cetera. A lot of business opportunities if you can lift off of the Earth inexpensively, daily, on an infrastructure. And then at the apex anchor at 100,000 kilometers, and by the way, you can pick almost any number you want. At 100,000 kilometers, you can climb up there, and then from there, go almost any place in the solar system very easily. If you get up there, it's about 14 hours to the moon from there, with the velocity that you inherently get from the rotation of the Earth. 14 hours to the moon. I mean, amazing. Of course, it does take you 2 weeks to climb the tether, so it's not like the total time is less, but you can have a nice little infrastructure where you send stuff up and then deliver it to the moon. And, you know, this thing is not working as well as it should, especially when I just lost my screen here. Okay, that's not good. Let's go up here. Well, that's fun stuff here. There we go. I'm back. I'm back. Okay. So let's see. I go back out here. Okay. So we're here in the apex anchor, and then you come into what's the purpose of Galactic Harbours, and it's really to flourish, develop entrepreneurial space. The transportation is the first mission, but everything else falls out. Space-based solar power is one that should end up. So we just saw this chart about breaking out from space elevators to Galactic Harbours and recognition that we can do things. Let's look at what's going on today in the 20s. We're talking about phenomenal movement off planet. And because we're having phenomenal movement off planet, we have greater needs for liftoff. And that's the real kicker. If we're going to fulfill our needs to go to the moon and Mars, and put solar, space-based solar power in GEO orbit, we need a way to get off planet. So what are the strengths of space elevators and Galactic Harbours? The bottom line is just think permanent infrastructure. The Japanese actually call space elevator a train system, and they call their tether the train tracks. So if you think that way, trains vertically, we're talking about a remarkable capability. And then, of course, the second aspect of Galactic Harbours is we will enable new missions. You can't do it today because it's too expensive, too heavy, too something. Space elevators and Galactic Harbours will enable all that kind of stuff. So what's the case for space elevators? Permanent transportation infrastructure, daily, rapid. By the way, we can get to Mars in 61 days. Environmentally friendly, and we have the material. So we really believe that the space elevators are there. Now, if you're really interested in space elevators, I highly recommend you go to our website, lulu.com, I'm sorry, isic.com, or I can get this right. Isaac.org. Anyway, we have 11 studies there that we've done, year-long studies with a bunch of experts. We've come to conclusions about all these different topics. So if you have questions about the tether climber, the Earthport, roadmaps, tether material, we have year-long studies on all those things. Just go to our website and you can download those for free. There's also some studies made by the international group I talked about earlier. The latest one is the Road to Space Elevator Era, where we looked at each of the technologies needed, ranked them on TRL levels, and talked about the system level of expertise and where are we. Where are we is the question. Engineering development. We're ready to move out of the technological feasibility arena. We believe we're ready to start testing. We need to move into the next box and start doing engineering validation. And of course, that will require an in-orbit test of a long tether with tether climbers going up and down. We figure we can do that in like 5-6 years. The long pole in the tent, of course, is our tethers, and we got a lot of work to do in the tether arena. I don't want to short stack that one. That's going to be a big challenge. But we have a tether material that's ready. So the IAA study answered a lot of the questions your Earthport is ready to do. Who can't do a floating platform? All you need is a reel in, reel out capability and an ops center. Headquarters, anybody can put an ops center together. I actually helped do one of those things. But anyway, engineering models for the tether climber have a lot of challenging. We've got to do wheels that'll go 100,000 kilometers straight up. We have to do the friction. What's the coefficient friction of single crystal graphene? We really don't know that. We've got a ways to go. A lot of questions. The GEO node is a phenomenal opportunity to start businesses for low-cost access to GEO. Apex anchor, a lot of challenges there, but essentially we need a reel in, reel out capability and thrusters so that we can moderate the motion of the tether by being on the end of it like a piano wire, shorten the wire, or more like a guitar string, shorten the wire, lengthen the wire, you get different frequencies on the tether. The material, I believe, is ready to start. We got a lot of testing to do. We just finished our second assessment of the survivability from space debris. But NASA was nice enough to give us an estimate of the debris density that would be there in 2030 when these constellations like OneWeb, et cetera, are going to have 30,000 more satellites up there. So they gave us numbers of density in space, and then we calculated the probability of conjunction. And we believe that the space elevator and space debris can live together pretty easily. It definitely has a lot of little challenges, but nothing's too hard to do. We can do all that kind of stuff. The beautiful thing is space is awful big. Okay, a few charts on the carbon nanotube, the graphene stuff. The whole focus today is the upper right-hand corner, two-dimensional, one atom thick. They've laid these out in about 3 universities where they've shown that they can do a 0.5 meter long, 10 meter wide, 1 atom thick, single molecule. They've done this repeatedly at different places. It was first done in Beijing. Now the theory is you heat it up a little bit, you grab one end of it, and you pull it out of the furnace, put methane in at the other end, the hydrogen goes off, the carbon adds to the end, and you can just have a continuous length of single crystal graphene. And my friends working on this have joked that, hey, do you want a 100,000 kilometer molecule? Now, that's a little bit beyond comprehension, but scientists are always fun to talk to. Okay, this is the comparison of the strength on the left and the density across the bottom. That's what we need. To hang something from GEO, you need a very light material. And of course, you need something really strong. So the graphene, the single crystal graphene, fits right over where CNTs, carbon nanotubes, were and everything else. They still have those same characteristics. Very, very strong. Okay, so the answer is yes. Single crystal graphene is great. This is the concept that has been proposed for making a 100,000 kilometer reel of graphene. There are a lot of issues there, engineering wise. I know. How do you separate the two? They bond vertically, all kinds of issues. We've got a lot of issues. There's no doubt about it. But you don't have mega project success unless you take on a lot of these things. Okay, what's our vision? Our vision is to look at a global network of 3 galactic harbors, each with 2 space elevators in them. Now, initially, we believe we'll be putting up 14 metric tons of cargo, and then we'll mature and grow, maybe put a second tether in, or just grow the single material one way or another. And we would end up with 79 metric tons every day for each space elevator. So multiply 79 times 6 times 365, and you get the number on the chart there, less than 180,000 metric tons a year. Now remember, this is on a train track. This is a permanent infrastructure. So you just keep sending stuff. And if you want to supply Elon Musk his colony on Mars, this would be the way to do it. So what we've done is we've taken a look at the immense needs out there in the future. The first one is geosynchronous traditional missions. We got a lot of those. We can do those today, but we have a lot of new missions at GEO. And then we have interplanetary missions with people instead of little satellites. So there's a lot of stuff coming up. The IAA report back in 2014 kind of quantified what we'll say is mass to GEO and beyond per year. So you can see space, solar power, holy Toledo. That's a lot. A lot of other things are there, nuclear material disposal. There's a lot of missions there. We can't satisfy that list even with our robust 6 space elevators. That is a remarkable look at the future on what we need from space. So what are the needs for interplanetary flights? Well, you'd like to have a lot of mass sent to your location. Elon Musk was quoted as saying he needs 1 million metric tons on the planet to support his 100,000 person colony. 1 million metric tons. Divide that by his launches and you'll figure out it takes a long time to do that. Oh, by the way, the study done by Arizona State University that looked at release from the top of a space elevator going to Mars, we had multiple days where we could get there in 61 days. Now, there were many days that it took over 300, a lot of those things. But the kicker was we could launch every day. We could lift off the surface of the Earth every day, 365 days times 26 months, because you've got a launch window for Mars that separates opportunities by 26 months. We can lift off every day going to Mars. It's a different path every day, but it can get there. Many of them early, 61 days, some are around 79 to 80, which are really fuel optimized also. So we have massive movement, rapid transit, and daily launches going to Mars, a remarkable strength. So we picked 3 reference missions, trying to get a real feel for how this works. If we used rockets and space elevators as a cooperative and compatible, infrastructures, architectures, we could make a cut at supporting these missions. So we got 5 million metric tons from John Mankins, who is running the space solar power around the globe right now, as the need for support to 12% of the global population and eliminate hundreds and maybe even thousands of coal plants. The Moon Village is an estimate of 500,000 metric tons, and SpaceX, we got that number from Elon Musk, so we've got big numbers there to satisfy. Rockets would have a hard time doing that. So if we have a new paradigm where we can launch every day, release every day toward Mars, we can get there in 61 days sometimes, and we can ship a lot of stuff. We're talking about a tremendous capability to support humans' movement off planet. So this is the way it looks right now in the sense of velocities as you go up the space elevator. Just recently, I came to realize, this is like in the last week, I extended the space elevator to 163,000 kilometers long. And I said, what does that do for you? Instead of 100,000, which is kind of arbitrary anyway, go to 163,000 kilometers. When you release from the space elevator at that point, you have enough velocity to escape the solar system. So literally, I can put a science satellite at the top of the space elevator and go to any planet or any asteroid in our solar system just by releasing. No chemistry required. We don't need to get out of the gravity well. We just climb up with electricity. Okay, here's some cases and why we can get there in 61 days. We're not leaving the Earth's domain in the same vector as the Earth's direction around the sun. We're leaving at a different angle. You do a vector sum, you get a velocity. You can cut across the orbits and get there fast. It looks something like this. Anybody can, ask me questions. I'll solve the equations. We've got all kinds of opportunities. That's why you can do it 61 days sometimes. And sometimes it might take 380 days or 400 days. But the kicker is it's logistics. You don't care when the hammer was sent. You just want it there when you need it. Now, this is the optimum case done by Arizona State University, and they came up with 71 days with almost no fuel required for plane changes. They did have to have a fuel to slow down when you get to Mars. But that's 77 days. That's a heck of a lot better than 7 months. And then the curious thing happened. A friend asked me, well, if you can do it every day, why don't you have a bus schedule? And I said, hot dog, great idea. So we came up with a bus schedule. The Indian Ocean, the Pacific Ocean, and the Atlantic Ocean space elevators, we could pick and choose. So you pick and choose and you figure out how long it takes to get there from any one of them. You schedule it, you send your cargo to that one, you release on time, you go wherever you want. The concept of a bus schedule to Mars blows me away. Okay, this chart's too complex. Let's look at this one. If we want to support the 3 missions we've talked about, the reference missions, 5 million metric tons, 1 million metric tons, and 500,000, we can divide by the throughput of each of the galactic harbors. If we have 3 galactic harbors with full maturity, we can satisfy the Mars support in 6 years. 6 years, he can't even build it up that fast, but we can get him his 1 million metric tons in 6 years. Now that's assuming we grow to the larger, fuller capability, which would probably be like 2050 or 2055, but it's still a very bodacious amount of capability. Okay, the next section's a movement toward commercial. Most of you guys know this stuff, so I'm not going to worry about it. Basically, the news is that we have billionaires investing in the future of space. Now, it's kind of been subtle for a while, but then all of a sudden, Jeff Bezos and Elon Musk and Virgin Galactic and all those guys are jumping out there, and we've got big money available to move off planet. Revolutionary ideas like reuse of first stage and stuff like that. Unbelievable. We've got Elon Musk idea. We've got his contracts for Falcon 9, which really, he has a backlog for Falcon 9s and Falcon 9 Heavies that's awesome right now. Jeff Bezos, as I said, going to be a trillionaire. I think he can continue doing his little rockets. Then, of course, we have humans to the International Space Station by commercial companies. Now, that was a public-private arrangement, not purely commercial, of course, but it's still an awesome capability. May 27th, if the hurricane doesn't come in and ruin the launch capability, launch at the Cape. Here's pretty pictures of our different competitors, Boeing and SpaceX. We've got those activities. So the question on will space elevator developments be commercial? Well, I guarantee you it's going to be a big question. A lot of benefits coming from space. Now, these next charts I kind of like put in here as discussion points if we had time. We really don't have time, so I'm going to go through them fast, and then we can get to some questions. I've got a few charts here showing who's playing in space. Space agencies with sounding rockets, manned spacecraft, that'd be human spacecraft, country with satellite ops. Oh, by the way, next year, Miramar will be the next one coming in. So everybody keeps getting satellites to operate in spaces as a prestige activities, astronauts and others. Then we have, I've got 3 or 4 charts here for money. The bottom line is there's a lot of money going into space. Okay, 3 choices. Government owned and developed. Well, think space shuttle. Commercially developed. Think Tesla, SpaceX. Then you've got a private approach like, a bridge with the toll road. There's no reason why we couldn't have private investment on a space elevator and then charge a toll for every trip. I mean, it could be done. So what are the conclusions? The material's ready. We're ready to move into the second blue engineering box. We're ready to join the discussions on how to get off planet. And we need a Space Elevator Institute. I'm kind of like working on that type of thing. That would be really neat to have some good academic clarity and investigations. Here are a bunch of questions. But the bottom line is space elevators, I believe, are closer than you think. In the last decade, we've done a tremendous amount of work. In the last 2 to 3 years, we've kind of focused and really gotten to the point where we feel very confident that we can build a space elevator and start pretty soon. And then I always like this image. And then I like the words even better. A friend of mine wrote those and I stole them. Apex is where the harbor, Galactic Harbour, meets the shoreline of outer space. We truly are a harbor, and we're going to be going out to the outer space. And it's where the transportation story of the 21st century meets the final frontier. I mean, it really is an awesome time to be alive. The movement off planet is really alive and well and is charging ahead. So I think each of us has an opportunity to look out there and really enjoy the future. It should be awesome. Okay, so why don't we see if there's any questions here. Any questions? We can either turn your mic on and jump in. I don't think we have that many people. So you can use your mic, or if you want to put it on a chat, either way, whichever you'd like. Who's got the first question?
I'll go. So
Go ahead,
is any funded studies to do some demos or anything? What's the next step? What's the real step in terms of hardware? I think you got a lot of wishful thinking here.
Now you're getting into the engineering stuff. Okay.
Of course, I'm an engineer.
The first thing is the U.S. is not putting any money into it. It's all volunteer in the U.S. The Japanese put like 200 million into it last year for space experiments. They flew some materials for the tether, carbon nanotube, stuff like that, and they flew a space elevator. Now, that was, by definition, 2 CubeSats separated by a tether with a third CubeSat that would climb between the 2 of them. So it literally was an experiment in space showing the capability to climb back and forth between endpoints on a tether. And it was a pretty neat thing. They got it all done. They got it to the space station. They deployed it out of their little shooter in the space station. It went out and the communications link broke. So they don't have a clue whether it deployed, whether the little climber climbed up and down or anything else. It's just a communications break in the link. But they have money for research and engineering and stuff like that. We're hoping to have some funding in the near future for the Space Elevator Institute. And then the first product that I can see coming out of a Space Elevator Institute is a funded demo in space. Now, Michael, you'll enjoy this one. 1,000 kilometers centered at 2,500 kilometer altitude. So it's in the radiation belt, but there's no debris or anything. And you have a 1,000 kilometer tether, and you have tether climbers going up and down, and you have a deployment from 0 tether to 1,000 kilometers. It could be an awesome demonstration of capabilities.
Yeah.
And so, yeah, that's what I would like the Space Elevator Institute is to have one of its principal thrusts.
Thanks.
Any other questions?
Yeah. Hi, Peter. This is Colleen.
Yes.
Why wheels? I mean, there's other ways to go up and down a tether, even or even to actually have like an actual elevator where the tether is actually moving, itself. Why did they decide on wheels?
Okay. First rule: nobody's decided on anything.
Okay.
What we have is we have good ideas that we've selected and put together in an architecture, and we claim this is a real architecture today. But quite frankly, when somebody gets paid $1 billion to design the space elevator, let's say the Japanese do that, and Obayashi Corporation, who've already designed it to a preliminary level, if they got $1 billion from somebody that said, go build a space elevator, here's the first $1 billion, they would have a lot of questions. And there would be a lot of issues that we have to talk about. A lot of people talk about electromagnetics, using the tether as one charge and then using a maglev type thing and doing that. I think that's a little heavy, but that'd be okay. We've got a good, well, the St. Louis NSS chapter had Larry B, whatever.
Yeah, and Larry is on, by the way.
Oh, Larry, well, welcome. You could talk to that. Larry did a really good engineering analysis of the wheels and how they would work. And he was talking about wear and tear and friction and all that kind of stuff. Larry, you want to talk a little bit about engineering choices on the tether climber?
The problems that we've seen before with using like traction, electromagnetic traction, is the current in the tether. We've never been able, because it's not a superconductor, there would be a lot of I²R losses. I focused on wheels. One thing I can tell you for absolute sure, you don't need tracks, but wheels is a very straightforward, ancient way of getting enough traction on a road. So,
yeah, and the Japanese like the word train, so that implies. But the wheels on the tether climber is just one aspect of all the engineering that has to be assessed and worked. And there are many, many, many questions that have to be worked on. We believe we have a pretty good handle on the issues and how we would address it, but it would sure be nice to have somebody give us initial funding to start a program. I've been through 3 mega projects where I started at the beginning and went 2 of them to the end. And it is really an exciting, awesome ride to go from a concept like we have right now to reality in 15 years. And it will be quite different. There will be a lot of decisions made along the way that we don't even see the issues today. So, it'll be interesting, but we're just talking about wheels today. Some of the designs for tethered climbers have, one of them had 12 wheels on each side with 2 tethers between them, so that you'd have 12 wheels and run them through in like an S curve or something like that. Many people have ideas. We don't have any money to go make decisions and start testing. Another question?
I'll ask one. So what is needed next to make this happen? Is it funding, educating young engineers and scientists about space elevators, or something else?
I'm really the wrong guy to ask, because I failed miserably on getting money for this over the last 10 years. But anyway, I believe what we need is we need to initiate a Space Elevator Institute. Once we've initiated a Space Elevator Institute, then a lot of questions can come to the forefront and people could start asking them. And then at the Institute, we would run a parallel study by the leadership of the space elevator community, and it would be how to start a program. So we would have a bunch of academics and experienced people addressing individual issues, like how do we develop a demonstration in space? And how do we test the wheels on current single crystal graphene test setups. And things like that. We can have the Institute starting to really ask the tough questions. We can have a parallel effort starting to lay out the programmatics, and then we can have a combination of incoming money for both of those. So I think the idea is to have an institute first. And we've started the initiation, but I think if you had probably $30 million, you could get a really nice institute at a good university that would be recognized.
I probably shouldn't ask, but do you have a university in mind?
Well, I live in Phoenix, and I'm working with the, they have an organization called the Interplanetary Initiative. They have a school that's called, let's see, the School for Earth and Space Exploration, SESI, School for Earth and Space Exploration. And they have a lot of stuff, and their chancellor president, Michael Crow, is a remarkable individual who likes to take risks and push the envelope for the future. So I'm really, really looking at ASU, but other universities have a lot of strengths. You know, USC has a lot of stuff, and these are just the ones I'm associated with. MIT has always led in astro aero. So, you know, it depends on which university would like to step up and say, I can handle this. You know, we can do a lot virtually, as we've proven now. And then, of course, the Center for the Single Crystal Graphene is Manchester, University of Manchester right now. So that'd be a good one to have them focus on it in parallel with the material. Okay, any other questions? We've got so many issues we have to address. Anybody who wants to participate, you can go to our website and you can look at the list of studies there. We've got 2 ongoing studies. One is environmental impacts, beneficial environmental impacts for space elevators, and the other one is the interplanetary missions, how we define the interplanetary missions. So we got 2 studies ongoing.
Okay. Let's see, Rob and Rick have their mics on. Does either one of you want to ask a question?
Yeah, I did have one. You mentioned 40 kilometers for separating these cables.
Right.
Is that just so that they don't bang into one another over the length of it, or?
Yes. It turns out they're radial out of the center of the Earth, so they're bending away from each other as you go up. And so then you look at what's the dynamic reach of any major sine wave as you go up and down. And we've had a lot of dynamic studies that have shown that the envelope or the column of a space elevator would not be anywhere close to that. So we could very easily put them at 40 kilometers apart. But that's an arbitrary number depending on who wants to do it. You know, it has to do with running both space elevators from one ops center, one logistics center, one human location. We'll probably have Marriott Hotel there with, you know, McDonald's or somebody to pay for the food and everything. So how far do you separate them on the ocean? There are a lot of issues like that. As I said, this is a huge project. We don't have too many answers, but we've got some ideas, and we've got a preliminary architecture that looks pretty sharp. We'll go with any suggestions, though.
Hey, Pete.
Yes.
For years, you got funding from Microsoft, right? Doesn't Microsoft still sponsor the annual conference?
That stopped about 1.5 years ago. It turns out our real sponsor got really, really sick, and we didn't know he was really, really sick. And then he left the company, and we've tried to get back into the cycle where you get funding from Microsoft. We still get a little bit of funding here and there for Microsoft employees working in a 501(c) support. And we get some funding from the Seattle Museum of Flight when we have our conference there. But ISIC is really underfunded by a lot.
There was no direct interest from Bill?
As far as we know, no, there was no direct interest. I've always thought that that would be an interesting question for some of these people. I've you know, up there, right? We have our conference in Seattle most of the time. And when we have it up there, it's just right down the street from from Blue Origin. So I went in there on a different tasking last time I was there. And I had the fun of touching one of their reusable rockets that went up to 100 kilometers. It went up and landed 5 times. So they have it in the lobby showing what they've been doing. So I snuck up and touched it so I could say I touched something that went to space. And I've been thinking about maybe we ought to address, you know, Bezos or Musk or somebody else. We actually gave Elon Musk a copy of the first space elevator 4-year study by the International Academy of Astronautics. And he was in the room with my wife and I. We were the 2 editors on it. And he was in the room, and we gave it to him, and you could see in his eyes that he wanted to make a comment negatively toward space elevators. This was in 2014. And he politely said, hey, you guys must have done a good job here. It looks good, and et cetera, and said, congratulations, and shook our hands. But he definitely did not jump on the opportunity to say we ought to pursue this. So, you know, we need somebody who can really approach these type of people and say a little bit of money would go a long way here. Any other question? Yeah, I agree. Okay, well, you know, we don't need to stay around and stuff like that if you don't have any questions. I've really appreciated this opportunity to share my vision on where we're going. We are moving off planet. This would be a very good way to do it. And it will take a lot of money, but it's relatively simple. It's just a train vertically is all it is. Having built a lot of spacecraft, we could do this in a heartbeat. All we have to do is get that material and everything else falls in place. And there are no showstoppers except for the material right now. So it would be a fun project. I'd love to do it.
So Pete, what is the website again? The ISEC, is it isec.org?
Yeah, www.isec, International Space Elevator Consortium.org.
Okay.
Yep.
I just put that in the chat in case. Dave maybe doesn't have a microphone, so he chatted 2 questions. Do you see them, or do you want me to read them out loud?
Okay, I can see them. What would a 100,000 kilometer long graphene tether weigh? I don't know the number right now, but it's been calculated 7 ways to Sunday for the last 20 years. Basically, you could put a full reel, 100,000 kilometers, on one little Falcon 9 and get it to GEO, along with the rest of the spacecraft to deploy it. The carbon nanotube was the first calculation, and now somebody just did it with single crystal graphene and how much it would weigh. And I believe it was something like 3 kilograms or 2 kilograms. It's not very much. It really is an awesome small mass to move. And could we get carbon from the lunar polar ice to make the graphene tethers in space and lower them down to the ground? The answer is we might be able to create single crystal graphene at geosynchronous, and that would be one of the alternatives. I've seen designs for doing that. We don't have that in our architecture right now, but if you could do it at geo, just bring up the carbon or bring it from the moon or bring it from someplace else, you know, that might work. I don't want to throw out any good ideas, and that's a good one. I don't have any problem with having the furnace in space. Yes, if you have a space elevator going up, it will take angular momentum out of the Earth's rotation. And if you have 6 of them, it'll take 6 times. We had a student calculate that about 3 or 4 years ago, and he was a senior in mechanical engineering and did the calculations on angular momentum being consumed into the rotation of the elevators upon the Earth. And it was, I think it was 1,000 times less than the tidal slowdown of the Earth's spin. So significantly less than any real impact. It was really a very, very, very small number. And the guy was a senior in college and did a really nice job of presenting the argument and the amount of energy and everything else. So it would slow the Earth down, probably affect the time, but infinitesimally, not significant. Okay, no more questions. I want to thank Nikki and Christine for setting this up. Thank you very much. I had a good time. I hope you guys did. It's always fun. And I put my email on there. If you need copies of the charts or anything, let me know, and I can get them to you some way, and we can go from there.
Hey, Colleen, do you want to say anything before we go?
Well, just like to thank everybody for stopping by again this month, and we will have another one next month on, got a couple of things are kicking around here yet, but we'll figure out what we're doing, and we'll get that posted out there.
The last cat question is really good.
Oh, go ahead.
Are there any liability issues? Of course. Now here's a funny one. Okay, we've had some lawyers jump in and help us with space elevators, and they're really quite good, and they've talked about all kinds of things. But here's one that I remember that I think is really great. The law of space, Outer Space Treaty, and liability of your state, the state's liable for what it launches in space and all that kind of stuff. There's a law in that whole regime that says a spacecraft is not allowed or is liable when it runs into something that's attached to the Earth. Now, it was really talking about a roof or a cow. And as I remember it, we killed the U.S. debris killed a cow in Cuba one time. And one lady lost her house in outback Australia when a piece of debris came in and wiped out her living room. So the law was that you could directly point to a government and say they have to pay for repairs. But the new interpretation, if you talk about space elevators, which are attached to the Earth, is all space debris must miss the space elevator or they're liable. I love that one. Everybody in space is liable to, they must miss the space elevator. We don't have to get out of their way. They have to get out of our way. That's a legal statement by a lawyer from Japan, a space lawyer from Japan. So yes, there are a lot of liabilities that would go with any mega project, and you can imagine all of them.
Okay.
Yes, okay, let's talk to the one that everybody's intrigued by. What happens is if it's severed? Okay, it's probably going to be severed if you really say, where would it be severed? Let's pick 1,440 kilometers up. That's where the densest part of the debris is, roughly. It's also at 890 kilometers altitude, but somewhere in there, let's say 1,000 kilometers. If it's cut at 1,000 kilometers, we have a plan in place, or at least we'd implement it in ops, where the geosynchronous would immediately start reeling out new tether to lower the mass and get it to reattach on the Earth. So you could save the space elevator. The stuff below 1,400 is coming down. And if there's no hardware below it, like you've taken the tether climber and you only leave one a day, so it's gone up past the 1,400, within about 4 hours. If there's nothing below it, the tether will lay down on the Pacific, assuming it's a mid-Pacific, to the east, and it will just lightly feather down and not affect anything. And there'll be a cruise ship, that's CREW, cruise ship, that would then grab the tether on the bottom and reel it up and just go get it. If you have a space elevator climber on it below 1400, it's going to bring the tether down pretty fast, and it's going to go to the east and deposit itself to the east of the Earth port in the ocean. That's why we choose to have the space elevator Pacific location like 2,000 kilometers to the west of the Galapagos. So anything that would sever 1,400 kilometers below would not even come close to the Galapagos. So it would just go into the ocean. And we'd reel in the tether and then see if we could pull up the hardware. But yes, we'd be liable for any damage of that hitting anybody coming down. But once you get above 2,000 kilometers, the odds of space debris hitting it are slim and none. And the odds of getting hit by an asteroid or something are slim and none. The real issue for SEVER is the space debris below. But we show numbers in our reports that say it probably won't happen its full life of the space elevator, because we can move it and we can design it so that it takes the personal hits, small space debris. You take the hit and just have a hole in it, and then you have a inspector tether climber, and it goes up and it fixes and patches and stuff like that. So we've got plans on taking care of little holes in the tether, and we have plans on saving the tether apparatus if it's severed at 1,000 miles up. So, you know, meanwhile, we plan on those, but the liability is there. There's no doubt about that.
Yeah, one of the other things I heard along those lines, like say it doesn't break, but the fact that the wind's blowing by that thing, you basically have a very long guitar string.
Yes, there's a lot of dynamics, a lot of dynamics.
Yeah, and then we wondered, like, you know, the vibrations, you know, there's not even any studies on the vibrations coming off that string where it's in the atmosphere.
Probably about 100 studies. Turns out if you go to our website and you go on to references and citations, we have 750 references put into categories: architecture, dynamics, earth port, tether climber. So you can go in there with any question you want in any component of the space elevator, and you'll have, you know, 40 to 100 references on that particular topic. Everybody loves to do the dynamics of a long tether, so there have been a lot of those studies.
Yeah.
Okay, one question's about graphene crystal is strong enough for the Earth-based. Heck yeah, man. It's so strong you wouldn't believe how strong it is. We can do the space elevator on the Earth. Now, one of the big questions that everybody has is, should it be the first one on the Earth or the Moon and the Mars? My answer is we're going to have space elevators on all three of them, as well as other planets. The kicker is there's no demand if you can't get off the Earth. And if we're using rockets to get out of the gravity well, we're going to send 3 people every 70 years. We're not going that fast moving off planet if we're using rockets. If we use space elevators, we'll have a robust movement. And then we first put one on the moon, another one on the moon, and then we put one on Mars, and we have an infrastructure where we ship stuff from the apex anchor on the Earth space elevator to the apex anchor of the lunar elevator, and then you lower it to the surface. So space elevators are doable at all the different locations, but we really have to get a robust movement off of the planet Earth, and having a train do it would really work a lot better than individual rockets. Oh, and then Rick asked whether we can generate electrical current. Of course we can. We're going to have material going through magnetic fields that are changing in magnitude and direction constantly. The answer is not can we create it, but is there too much? And how do we control it? And how do we deal with the electricity? I really am curious about that issue. The good news is we have, as our vice president for ISIC, a gentleman, Dr. Dennis Wright, who has an expertise in electromagnetics of outer space. And he's looking at that question. What's the coupling like? What would be the voltage buildup? What would be the current flow on your tether material? And of course, one of the real questions is, what's the conductivity or resistivity of the tether material? And we don't know that to the level we need to. So we really need to look at that. And it's a big question. Now, is the space elevator electrical current, could it be a clean energy source? Well, yeah, it could be. I really think what we want to do with the space elevator is put geosynchronous satellites called space solar power up there, capture the energy at geo, ship it down to the Earth. We can eliminate hundreds of coal plants by doing that. The guy that's leading that is John Mankins. Dr. Mankins retired out of NASA, and he's got 2 or 3 organizations working that. You can go on the web and ask space solar power. A phenomenal amount of work has been done. I would recommend, if you're interested in supplying clean energy to the surface of the Earth, excellent background. Go through and look at that stuff. Okay, well, it sounds like we've gotten rid of all the questions, and it's 5 o'clock. We're probably a little bit beyond, but I do appreciate the opportunity to talk about my favorite topic. Of course, golf's my favorite topic, but I'll make do for this.
Okay, yeah. Well, thank you so much
Okay,
for
thanks, Nikki.
stopping in here, Peter.
Yeah, no problem. This is fun.
Okay.